speaker, Johannes Nordström from Bath, and he will talk about rational homotopy theory of closed 7 and 8 manifold.
Thank you very much for the invitation to speak here at this workshop. I've greatly enjoyed both the science and the location. The topic of my talk is a little bit of a topological tangent to the main theme of the workshop. But as you can maybe guess from the dimension 7 and 8 mentioned in the title, the motivation comes from trying to understand something about the topology of manifolds with exceptional holonomy. So what I'm talking about is joint work with Dermot Crowley and Csaba Nagy, who are both topologists. So the 7-dimensional part is based on a paper with Dermot, and Csaba and I are currently writing up the details of the 8-dimensional part, but there is an archive preprint that has some weaker versions of the statements that I will make in this talk. So rational homotopy equivalence is a weaker notion of equivalence than homotopy equivalence, but it's sometimes useful as a sort of first step towards trying to understand homotopy equivalence and diffeomorphism questions. Basic invariant that you can use to try to distinguish between topological spaces up to rational homotopy equivalence is massive products. But one feature of massive products is that they involve making some choices. So there's some are only defined up to making these choices. So there's some ambiguity, and that can make them a little bit hard to work with. So the starting point for the talk is that to observe that by taking a massive product and then multiplying by some further class, just taking the crop product in the cohomology algebra, with some further cohomology class, you get something that reduces the amount of dependence on the choices. And by then changing perspective a little bit, you can reinterpret what you get as some kind of tensor that actually captures more information than the massive products that you started with. And a lot of the time, or at least in some dimension ranges, these tensors actually are very useful for formulating and proving classification results. So as an overview of the structure of the talk, so first I'm going to talk a little bit about the bare basics of rational homotopy theory and what it means for a space to be formal, and the simplest kind of massive products, which are massive triple products. Then I'll move on to how to reinterpret massive triple products as a tensor, which I call the Bianchi-Massey tensor, because the symmetries that it has are related to the Riemann curvature tensor and the Bianchi identity there. And then how you can use that to get a nice statement for classifying simply connected 7 manifolds up to rational homotopy equivalence. Then I'll move on to something a bit more complicated, which is about how you can do something analogous for starting with 4-fold massive products, reinterpreting that as a tensor, which I'll call the pentagonal Massey tensor, and then use that to say something about classifying simply connected 8 manifolds, or at least detecting their formality. And then if I have time at the end, I'll try to say something about the slight complications of how the pentagonal Massey tensor still depends on choices. So going through this process doesn't completely eliminate the choices, but it makes them more manageable. Okay, so starting with the basic notion of rational homotopy equivalence, by Whitehead's theorem, homotopy equivalence between spaces is basically the same thing as a continuous map, such that the induced maps on all the homotopy groups are isomorphisms. So the notion of a rational homotopy equivalence map weakens that to just saying that you get isomorphisms after you tensor with the rationals. So you kind of throw away all the torsion information. Now, this notion of a rational homotopy equivalence map, saying that you have a rational homotopy equivalence map from one space to another, that relation is not symmetric. It doesn't guarantee that you have a map going the other way. But you can still make a notion of, you can still turn that into an equivalence relation by saying that 2 spaces are rationally homotopy equivalent if there's a zigzag of these rational homotopy equivalence maps between them. So this is a weaker notion of equivalence than, obviously, than saying that your spaces are homotopy equivalent. But it's a useful first step, and it turns out to be turned into questions about rational homotopy equivalence turn out to be transformed into just questions about algebra in a very nice systematic way. So specifically, you can turn them into questions about commutative differential graded algebras. And the process is kind of simple. You should basically just think of it as starting from a manifold, considering it's the Rahm complex of differential forms, which is a commutative differential graded algebra. That's something that computes for you, in particular, the Rahm cohomology, or equivalently the cohomology with real coefficients. But looking at the complex differential forms, you can also cook up some other extra structure on the Rahm cohomology. Now, if I was talking about real homotopy theory of manifolds, it would be enough to just say that I'll talk about differential forms. If I want to talk about rational homotopy theory, then I need to do something a bit more in order to cook up a commutative differential graded algebra of the rationals that can compute for me the rational cohomology. But there is a way that you can do this. If you start with a simplicial space, then you can kind of make a pretend version of the Rahm cohomology by defining these piecewise linear forms. And that gives you a commutative differential graded algebra that computes for you the rational cohomology. So all the questions about topological spaces and rational homotopy equivalence between them can be transformed into questions about commutative differential graded algebras and quasi-isomorphisms. So quasi-isomorphism between commutative differential graded algebras is just a homomorphism of the commutative differential graded algebras, such an induced map on the corresponding cohomology or isomorphisms. So the upshot is that once you've proved some basic fundamental theorem in the area, it just tells you that questions of rational homotopy equivalence of spaces are or at least nice enough spaces like manifolds or simplicial complexes are equivalent to just questions about classifying or understanding commutative differential graded algebras up to quasi-isomorphism. Now, one of the advantages of working on the algebraic side is that if you're talking about topological spaces, it's not so clear what it means to have the simplest possible topological space with a given cohomology algebra. But on the algebra side, there is such a thing, namely the simplest way to get a commutative differential graded algebra with a prescribed cohomology algebra is to just take the cohomology algebra itself as your algebra and define the differential to just be 0. That's obviously the simplest differential graded algebra that gives you that cohomology ring. And then if your commutative differential graded algebra is quasi-isomorphic to such an algebra with trivial differential, then you call it formal. So basically, the formal algebras are the ones that have the simplest possible quasi-isomorphism class with a prescribed algebra. And then on the translating that back to the topology side, it also gives you sort of a notion of the simplest possible rational homotopy class of topological spaces with a prescribed cohomology algebra. Now, one of the amazing things is that this shows up in the context of Kähler geometry. So Deline, Griffiths, Morgan, and Sullivan proved in the 70s that any closed Kähler manifold has to be formal. Or slightly more generally, any complex manifold that satisfies the DD bar lemma has to be formal. So if you like, this means that if you have a Kähler manifold and you know its cohomology algebra, then you also know, because it's formal, that also uniquely determines its rational homotopy type. And the name formality comes from, the term formal comes from the phrase that if you have a Kähler manifold, then its rational homotopy type is a formal consequence of just knowing its cohomology algebra. Now, you can think of Kähler manifolds as being an instance of manifolds with special holonomy, of course. And the proof of the theorem involves playing around with Hodge theory. You have something like Hodge theory for other special holonomy manifolds as well, so that raises the question of do you also get a similar theorem for other special holonomy groups? Now, some of the other special holonomy families are related to Kähler manifolds, so you can various degrees of difficulty, you can deduce some statements, for instance, for hyper-Kähler and quaternionic Kähler from the Lean-Griffiths-Morgan-Sullivan theorem. But the main difficulty is what about the exceptional cases? So 7 manifolds with holonomy G2 or 8 manifolds with holonomy spin 7. So that's what I'm interested in. I'm interested in trying to figure out what are the topological constraints for a 7 manifold to admit holonomy G2 matrix. If one could prove that G2 manifolds are always formal, that would be a very strong constraint. One way that you can go about this is generate a bunch of examples of holonomy G2 manifolds, then test whether they are formal, and if you find one that isn't, then you've disproved your conjecture, so then you would be done. But if you want to do this in a systematic way, then it would be really nice if you had a sort of a clear-cut test that told you what exactly do I need to compute for my 7 manifold in order to decide whether it's formal or not. And you can use massive triple products, for instance, to test. If you find a non-zero massive triple product, then that is something that tells you that you're not formal. But I wanted something that would actually tell me what exactly do I need to prove that would tell me that I can stop looking for a non-trivial massive triple product. I wanted to have not just a necessary condition for formality, but necessary and sufficient conditions. So this project is kind of about finding some nice invariants that can help you decide whether your space is formal, especially something that will work for closed, simply connected manifolds in dimension 7 and 8. So I'm not going to say too much about massive products, but I'm going to say something about massive triple products, and later on I'm going to talk about massive fourfold products. But the triple products are the most basic case, so I'll explain this in a bit more detail. So massive triple products are a kind of extra structure that you get on the cohomology algebra of your commutative differential graded algebra. So as I said, you can think of this commutative differential graded algebra as just being the de Rham complex of the manifold that you're interested in, something like that. And I'm going to focus on taking products of degree 2 cohomology classes, because if I'm thinking about a simply connected 7 manifold or something, then the degree 2 cohomology classes are the lowest degree that I could possibly I could multiply classes together. And by sticking to that degree, I can avoid sticking in lots of minus signs to try to say whether something commutes or anti-commutes depending on degree.
So for clarity, the products you're talking about at the beginning are just cup products?
So I'm doing cup products in the cohomology algebra, but I'm also taking sort of co-chain referentially, and I'm taking differential forms, if you like, representing my de Rham cohomology class. I'm taking wedge products of those differential forms. So to define a massive triple product, what I need to start with is a triple of cohomology classes, such that the products of 2 of them vanish and the products of another pair also vanish at the same time. So that means that if I pick some, say, differential forms representing these cohomology classes, then if I take the product of the first 2 differential forms, I get something exact. So I can take a pre-differential of that. I can take a differential 3 form whose exterior derivative gives me that wedge product of 2 forms. And similarly, the wedge product of the other 2 gives me something exact. So I can pick a 3 form as a pre-differential for that. And then if I take a suitable linear combination of, if I take this product alpha 1 wedge gamma 2, 3, then the differential of that will be alpha 1 wedge alpha 2 wedge alpha 3. And that's the same as the differential of that. So when I take the difference, I get something that's closed. Hence, that's going to represent some other cohomology class, now in degree 5. The problem with this process is that it involved making a bunch of choices. And if I change the choices of pre-differentials, I could end up with a different cohomology class. So we could either say that this is something that's only defined up to choices, or we could consider the set of all things that we can obtain if we are allowed to vary the choices in the definition. So this notation here will denote the set of all possible things that I can obtain by that procedure. So that will be some non-empty subset of the degree 5 cohomology in this case. And it's easy to see that by changing the choices of, if you, for instance, change the choice of gamma 1, that the freedom you have in choosing that is you can add on a closed 3 form, and the result of the effect that will have on this cohomology class is you add on the product of the cohomology class represented by that 3 form times the class x1. So you can sort of shift the value of this triple product by x1 times any degree 3 class. Similarly, you can, by changing the other gamma, you can shift it by x3 times any degree 3 class. So all in all, what this subset is, it's a coset for this. You can do something similar, which more complicated, which I won't go into too much detail about. You can say if you have k cohomology classes and the certain products between them vanish and certain lower degree massive products between them vanish, then you can also define a k-fold massive product. So this will involve a bunch of choices, and to say that a massive product vanishes means that there's some way to make the choices in the definition such that the result vanishes. And if you start with a commutative differential graded algebra where the differential is 0, then no matter what choices you make, you're always going to, all these massive products are going to be 0. It's also clear that the property of your massive product being representable by 0 is something that's invariant in the quasi-isomorphism. So the upshot is that if you have one of these k-fold massive product that can't be represented by 0, then that's an obstruction to your CDGA being formal. Now, if we're doing this if we're thinking about a topological space, it's S-connected, so the first S homotopy groups vanish, then the lowest possible degree for a k-fold product would be something that takes k classes in degree S plus 1 and multiplies them together. That will then give you a product. The product of those will then live in degree ks plus 2. If you have a closed-oriented manifold, then the top degree, any massive product takes values in the top degree will automatically be representable by 0. So the upshot is that if you're looking at S-connected closed manifolds, then Poincare radiality gives you sort of a lower bound for what the dimension of your manifold must be in order for there to be a non-trivial k-fold product. In particular, if we're looking at simply connected closed manifolds, then have any non-trivial massive triple products at all, you need the dimension of your manifold to be at least 7. Once you move up to simply connected manifolds, closed simply connected manifolds dimension 8, then 4-fold massive products could also play a role, but 5-fold massive products won't play a role until you move on to simply connected manifolds of dimension 9 or above. So that's why, in order to understand the formality of simply connected manifolds in dimension 7 or 8, basically what we need to understand is how to capture some information related to massive triple products and massive 4-fold products. Any questions? Yeah.
I mean, in the G2 case, I assume from what you're saying that you don't have any examples of non-trivial massive products.
That's right. I've not yet found any non-trivial. I've not yet found any non-formal G2 manifolds.
I mean, is
So.
there any chance of working out the cohomology algebra for some examples?
Yeah, I mean, if you take some of Joyce's examples, for instance, you can, with some effort, work out what the cohomology algebra looks like, and you can start trying to compute this. But as soon as you move away from sort of the very simplest, in the very simplest examples, it's not so hard to see that these things will all be 0. In more complicated examples, well, it just becomes very complicated to actually do the computations. So it's if someone feels like getting stuck in and you're picking cochain representatives for all the cohomology classes on some of Joyce's orbifold resolutions, then I think you should totally go for it. Send me the answer in a postcard, please. And if you find a non-formal example and disprove this folklore conjecture, I'll be very happy to be a co-author in your paper once you've done all the hard work. All right. So the massive triple products will give you if you find a non-zero one, then you've proved that your space is non-formal. But the problem is that even after you've done the computations, you've picked your cochain choices, you computed this resulting class in the 5th cohomology or whatever, then you still have the issues, you still have to go back and check, well, if I change my choices, could I then change the result to become 0? So what I want to do is try to eliminate some of the dependence on choices. And that's not so hard to do in a way, because the massive triple product is a coset for, okay, I've wrote the wrong degree here, but it's a coset for something involves x1 and, okay, there's a bunch of 4s here, this should all be 3s. So it's a coset for x1 and x3. So if we multiply by a further class x4, whose products with both x1 and x3 are 0, then you're going to get something that doesn't depend on any choices, just as a single well-defined element. On the other hand, if the cohomology algebra satisfies 7-dimensional point radiality, then actually, if you know the product of your massive triple product with all such classes, x4, so whose product with x3 and x1 are both 0, then then you can recover from that the set of your massive triple product. So doing this extra multiplication to go from a degree 5 class to degree 7 class doesn't actually lose you any information if you're working on a manifold, on a closed 7 manifold. All it does is it goes from having a set of degree 5 cohomology classes to being able to do a single well-defined degree 7 cohomology class, which you can then integrate to get a rational number. So that makes things slightly more convenient. But what kind of object is this? Well, if all the products of degree 2 cohomology classes were defined, then this expression here would be well defined for any x1, x2, x3, and x4, because this condition would automatically be satisfied. And then what you would end up with would just be a tensor. So it would be a 4 tensor that takes sort of something in the 4th tensor power of the degree 2 cohomology and spits out something in degree 7 cohomology. But the problem is what happens if you have some non-trivial cup products between degree 2 classes. Then you're trying to define a tensor, but the domain is not a linear subspace of this tensor space. So that doesn't really work so well. So you have to do something, you have to change your perspective slightly to get something useful out of that. So let me set up a little bit more notation. So I'm using pk to denote the kth symmetric power of a vector space. I'm using E to denote the kernel of the cup product map from H2 to H4. So that's then a subspace of the second symmetric power of H2. And K means the kernel of some notion of symmetrization, which will vary depending on later on. But the point is that this sort of trying to be tensor M that I defined, this was defined in terms of taking a massive triple product and then multiplying by one more element, that was something that was somehow multilinear, but I couldn't interpret as a tensor in general, but I can factorize it into 2 steps. I can think of it as first doing a map that takes a quadruple of classes such that the product of 2 of them in sequence is 0, and sends that into the symmetric square of the kernel of the cup product map by doing this operation. And then I apply to this element here, I apply the operation of apply gamma to the first one, to the first of these, and then apply alpha squared to the second one. And the magic is that this operation here actually turns out to take closed values not just on the image of this cross map, but actually takes closed values on a linear subspace of the symmetric square of this kernel. So if I can have a well-defined linear subspace of the symmetric square of this kernel, which is I take the kernel of the full symmetrization map, and this expression here gives me closed values on that whole linear subspace. So hence I get a linear map from this subspace of the symmetric square of the kernel of the cup product map going into the degree 7 cohomology. And this linear map is not just defined given choices, it actually turns out to be completely independent of choices. In the same way that basically, because of the way that taking the triple product and multiplying by one more class gave me something that was completely independent of choices. This thing is also independent of choices, but this is now a bona fide linear map. And this is what I call the Bianchi-Messi tensor. So the Bianchi here comes from the fact that I'm considering something that's related to taking the kernel full symmetrization from symmetric square of symmetric square going to symmetric fourth power. So that's basically the same kind of gadget or something very closely related to Riemann curvature tensors. Any questions so far? Okay, so what properties does this have? Well, so it determines the trying to be tensor that I discussed before. And that, in turn, I said, would determine all the triple products under point radiality. So hence, this Bianchi-Messi tensor contains all the information on the massive triple products in the context where you have point radiality. On the other hand, if the image of this cross map spans this particular linear subspace, then the Bianchi-Messi tensor would be completely determined by the massive triple products, but that's not something that doesn't always happen. So you can have situations where the Bianchi-Messi tensor captures information that the massive triple products themselves don't actually notice. The Bianchi-Messi tensor has a nice functoriality property, and from that you can also see that this Bianchi-Messi tensor is an obstruction to formality. So if your algebra is formal, then the Bianchi-Messi tensor definitely has to be 0. But more than that is true. In fact, if you have a simply connected 7-dimensional manifold, or equivalently you're talking about a commutative differential graded algebra that satisfies 7-dimensional point radiality and the first cohomology is trivial, then all you need to know to determine the rational homotopy type is the cohomology algebra together with this Bianchi-Messi tensor. So you only need to compute this one thing, and then you're done. So in particular, this is also, if you're just interested in formality, this is a complete test for formality. So if you want to test whether something is formal, all you need to do is compute this tensor. If it's 0, then you're formal. If it's non-zero, then you're not formal. So it's both a necessary and sufficient condition. And ultimately, the argument here doesn't really rely on working with simply connected 7 manifolds. It works just fine as long as if you have an S-connected manifold, then as long as you're in a dimension range where massive fourfold products can't start to play a role, then you have an analogous result. So I'm kind of trying to market this as a useful tool. So here are the key points in my advert. So it's something that's completely independent of all the choices and definitions. That makes it more useful. You don't have to sort of go back and check, well, if I change my choice, would that suddenly become 0? It's in principle computable. I mean, you kind of have an explicit formula for how to compute it. It may, in practice, this can be difficult to evaluate, but you know what you need to do. It's not something that involves going through a long chain of, well, this is isomorphic to that, and that's isomorphic to that, up to some choices, which is the kind of argument you often end up with in rational homotopy theory. You know precisely what symmetries it has. So if you're looking at the massive triple products, then some massive triple products are related to other ones. But here you've kind of captured everything in a single tensor, and you know precisely what the symmetries of that tensor is. You know precisely how many independent components there are. You know basically how many rational numbers you need to evaluate in order to determine whether your 7-dimensional manifold is formal or not. Even though it's related to massive triple products, there are definitely situations, you can construct examples where there are no defined massive triple products because the kernel, there are not enough classes whose product is, degree 2 class whose product is 0, but nevertheless this tensor can detect non-formality. In the proof that this thing classifies things up to rational homotopy equivalence, you kind of do what you often do in rational homotopy theory. You find the so-called Sullivan minimal model, which is a unique isomorphism class in your quasi-isomorphism class. But it sort of wraps up all these arguments into the proof of this classification theorem and sort of shields the user from actually having to get your hands dirty with minimal models. So it kind of provides a nice user interface, if you like. You just have to compute this thing and you don't have to worry about the Sullivan minimal models. And finally, to round out the discussion of 7 manifolds, here's a sort of cute little remark that's relevant if you're looking at manifolds with holonomy G2. So manifolds with holonomy G2 have a hard Lefschetz property that you have this degree 3 cohomology class, just corresponding to the torsion-free G2 structure, such that if you take the product of that with 2 degree 2 cohomology classes, then that gives you a non-degenerate bilinear form. If the second Bethe number of your manifold is less than or equal to 3, then that automatically implies that your manifold is formal. And that's just a computation involving the symmetries of these tensors, and it turns out to be exactly the same computation that shows that the Riemann curvature is determined by the Ricci curvature in dimension less than or equal to 3. So that's something that I think is kind of cute. Any questions? Okay, so then I'm going to move on to the 8-dimensional case, and in dimension 8, we're going to have to start thinking about 4-fold massive products. So here's the definition of a massive 4-fold product. It gets a little bit more complicated. So now we need to start with 4 cohomology classes, such that the product of the first 2 is 0, the product of the next 2 is 0, the product of the last 2 is 0. That means that you can take the massive triple product of the first 3, or you can take the massive triple product of the last 3. If those also vanish, then you can define the massive 4-fold product. So basically, you first pick some representatives in order to compute the massive 3-fold products. You're assuming that those are 0, so you can pick some 4 forms that are pre-differentials for those, and then you bundle those into an expression whose differential then automatically vanishes. So it represents a degree 6 cohomology class, because I'm still restricting attention to products of degree 2 classes. But now you're making sort of a slightly longer sequence of choices, so that makes it more complicated to see what the dependence on those choices are. But one thing I want to emphasize is that if you fix the choices in the first 2 stages, then the remaining ambiguity from the choice in the last stage, so choosing these differential 4 forms, sigma, that still gives you some kind of coset like that. So that means that if we then take the product of your massive 4-fold product with a 5th element, whose product with both x1 and x4 is 0, then you get something that depends only on the choices of the alphas and gammas. Okay, so we can get so if we take the product with this 5th element, whose product with both x4 and x1 is 0, then we get something that only depends on the choice of alpha and gamma, and you can see this explicitly just by using the Leibniz rule to rewrite the product. So after using the Leibniz rule to rewrite this, you get something that's written in quite a symmetric way using just the alpha and the gammas. And now we can try to do the same kind of trick as we did with the Bianchi-Messer tensor, and we sort of factorize this expression as a product of 2 things. So first we have this nonlinear map that takes a quintuple of classes whose products vanish in a cycle like this, and we look at this expression, this cyclic sum of tensors. And then we try to compose that with a particular linear map defined in terms of alpha and gamma, defined on this tensor product. So again, this will now be a linear map from this tensor product going into the degree 8 part of your commutative differential graded algebra. And we would like to understand, is there some linear subspace on which this takes closed values and thus defines a map to cohomology? So we can now first consider the case where all the cup products are 0. So then this symmetrization map now defines a tensor. It defines a linear map from the 5th tensor power of the second cohomology into this tensor product. You can identify that the image of this linear map with the kernel of some particular weird symmetrization map. That kernel, well, it is what it is. You can compute its dimension. It's a particular representation of the general linear group, and you can identify what representation that is in terms of this description of representations of the general linear group in terms of partitions. But the point is that the image of this star map is always contained in the kernel of this map P. When there are some non-trivial crop products, what you should focus on is the kernel of this kind of symmetrization map P restricted to this tensor product involving second cohomology and the exterior square of the cup product, the kernel of the cup product. So that's always going to contain the image of the star map, but it doesn't have to be spanned by the image of the star map. Nevertheless, the restriction of this map alpha gamma squared that you cooked up from making the choices of differential forms alpha and gamma, that always takes closed values on that kernel. So the upshot is that you manage to cook up a particular subspace of a tensor product involving the second cohomology and the kernel of the coproduct map, and you get a well-defined, you get a map from there into the degree 8 cohomology. And that's now going to be something that captured all the information about the fourfold Massey products. So compared with the Bianchi-Massey tensor, the problem is that with the Bianchi-Massey tensor, going through this process completely eliminated the dependence on choices. In this case, we only eliminate the dependence on the last stage of choices. So we still have some dependence on the choice of alpha and gamma, but there are some, actually in quite a lot of the cases you care about, this dependence doesn't happen. So first of all, if there's no degree 3 cohomology, then you're completely independent of choices. And also, if the Bianchi-Massey tensor is 0 and you have in a point graduality context, then you also don't have any dependence on choices. Well, sorry, I should clarify that a little bit. You still have different choices, but when the Bianchi-Massey tensor is 0, you kind of have a canonical class of choices that gives you a canonical representative for this pentagonal Massey tensor. So then that's it. In one of those situations where you have a canonically defined pentagonal Massey tensor, then there's also sort of very nice functoriality relation for the under homomorphisms of commutative differential graded algebras. And you can then use that to say, for instance, that this is an obstruction to formality. So if your topological base is formal, then definitely you must be able to make the choices so that the pentagonal Massey tensor is 0. And moreover, if you have a closed manifold where the Bianchi-Massey tensor is 0, so that you have a canonical representative for the pentagonal Massey tensor, then that canonical one has to be 0 if you want to be formal. Now, if we go back to thinking about S-connected manifolds for some S greater than or equal to 1, so for instance, simply connected manifolds, then as long as we're in dimension range now where 5-fold Massey products can't play a role, then it turns out that the Bianchi-Massey tensor and the pentagonal Massey tensor together give you a complete, necessary, and sufficient condition for formality. So in particular, if you have a simply connected 8 manifold and you want to check is the simply connected 8 manifold formal, what you need to do is first you compute the Bianchi-Massey tensor. If that's 0, then you have a canonically defined pentagonal Massey tensor. You compute that. And if that's 0 as well, then your manifold is formal, otherwise it wasn't. What we kind of expect is that there should be, similar to the 7-dimensional case, this shouldn't just be a test for formality. We expect that it should actually completely determine the rational homotopy type. But we haven't proved that yet. Actually, it's kind of complicated to even state what it would mean for this thing to determine the rational homotopy type in generality, because of the fact that we still have this sort of residual dependence on choices. So if in a situation where the Bianchi-Massey tensor is 0, so that you don't have any dependence on choices, then it's easier to state the conjecture. Then the conjecture is just the rational homotopy type should be determined by the cohomology algebra and the pentagonal Massey tensor. But I will need to do a little bit more work in order to explain in order to just give some statement of the conjecture at the end. Any questions? Yes.
Can you use F or P to detect other things other than formality about UCG?
So,
Tell you more information. Does it tell you more? I guess it tells you more information than just formality.
yeah, so it tells you so, I mean, if you're in this, for instance, context of symplectic 7 manifolds, then it completely determines rational homotopy type. But even if you're working with some arbitrary commutative differential grade algebra, it still tells you something useful. So without point graduality, it doesn't necessarily even recover for you the triple products, but it's always something that's uniquely defined without any dependence on choices. So I guess I'm trying to market this as something that if you ever find yourself trying to do some rational homotopy theory, it should always be a good thing to look at. But I would say that, wouldn't I? Okay, so in the final part of the talk, I'm going to try to do, explain would be overstating it. I'm going to show you something about sort of how the pentagonal Messier tensor depends on. Sorry, I forgot that. Sorry, I had one more part before moving on to that, actually. Okay, so I want to say something about how this pentagonal Messier tensor relates to the classification of simply connected 8 manifolds up to diffeomorphism. So if you want to classify simply connected 8 manifolds up to diffeomorphism, then one basic case that you should be interested in is when the cohomology is concentrated in degree 2 and 6. So basically, things that have the cohomology of connected sums of S2 times S6 connect sum with themselves. So my collaborator Csaba Nagy, he classified these things up to diffeomorphism in his thesis. So basically, if you think of them the right way, then they form a group, and he identified what this group is. And this group has a free part of a certain rank, A, computed here, and it has a 2 torsion part, which also has some rank with more complicated expression. So the starting point for our joint project was basically noticing that the rank of the free part of this group is exactly the same rank as the dimension of the space on which the pentagonal Messier tensor is defined. So what we found was that actually, in this case, the pentagonal Messier tensor basically completely detects for you the free part of this group. So the pentagonal Messier tensor is, in this case, detects the non-torsion part of the diffeomorphism classification, which is something that you should expect more generally, because there's a theorem of Sullivan that says that if you specify basically the integral cohomology ring of a closed manifold, and you specify the rational homotopy type and the Pontryagin classes, then that narrows down the diffeomorphism type to finitely many possibilities. So this is kind of an instance of that. Once you've specified the pentagonal Messier tensor, which we think should determine the rational homotopy type, then there's only finitely many things left to pin down. In this case, it's just some 2 torsion thing. So one interesting question is, in this domain for the pentagonal Messier tensor, you always have an integral lattice, and you can ask, does the restriction of pentagonal Messier tensor to this integral lattice take integer values? In this situation, for these kinds of manifolds with cohomology concentrated in degree 2 and 6, the answer turns out to be yes, it takes integer values. And what we find is that actually any integer valued map on this domain is realized by one of these manifolds. Okay, so now eventually moving on to the dependence of the pentagonal Messier tensor on choices. I kind of want to show you some equations. I'm going to go through them too quickly for you to parse them. But the aim is not really for you to digest it. I'm just trying to give you some notion of how complex this dependence is. So the opposite is it's too complex for you to digest in the 5 minutes I'm devoting to it. But if you spent 20 minutes digesting it and you were trying to work through an example, then you would be able to do it. That's kind of what I'm trying to get across. But one of the things that makes the relation a bit complicated to explain is that it's not enough to just know for instance, the Bianchi-Messe tensor. You actually need to know something related to the massive triple products themselves. So you have to regress a little bit to some other things that involve choices. So we have to define kind of a uniform version of the massive triple product. So again, this is defined on the kernel of some symmetrization of some tensor product of spaces of cohomology classes. Once you have made somehow your uniform choices of co-chain representatives, so you have a linear map that picks out a representative for each degree 2 cohomology class, you have another linear map that picks out pre-differentials for the products of classes that vanish, then you can use that to define a linear map on the kernel of this symmetrization, so that it then induces a linear map. Sticking to degree 2 cohomology classes, this now induces a linear map from this subspace of tensor product into the degree 5 cohomology. This actually allows you to determine the Bianchi-Messe tensor. So if you like, it sort of contains more information than the Bianchi-Messe tensor, but it now encodes it in a way that actually does depend on the choices. But it also determines directly the massive triple products, because if you start from a triple of degree 2 cohomology classes that has a well-defined massive triple product, then you can also take a certain combination of those that puts you in the domain of this uniform triple product. Evaluating the uniform triple product, and that gives you a particular representative of your of that massive triple product. So it's sort of the uniform triple product is somehow something that once you made these choices for all cohomology classes, it picks out a representative for all the massive triple products at the same time. But this uniform triple product now itself has some dependence on choices. If you have two different choices of the alpha and gamma, then you can basically, the interesting part of how they compare is when you made the choice for gamma, that involved you had a freedom of choosing adding on a degree 3, a closed 3 form valued function to that. So basically, the difference between the choices encoded by a linear map taking values in degree 3 cohomology. You can encode a transformation rule for the uniform triple product in terms of this degree 3 cohomology valued function. So you somehow just take a product of that degree 3 cohomology valued function with the identity map on degree 2 cohomology to get a map going into degree 5 cohomology, and that's the difference between the two different uniform triple products. So in one sense, this uniform triple product doesn't contain more information than the Bianchi-Messe tensor when you have Poincare radiality, because the Bianchi-Messe tensor determines what the image of the map that sends a choice to the uniform triple product. But the complication is that if you want to express the transformation rule for the Pythagorean-Messe tensor, you actually need this uniform triple product and not just the Bianchi-Messe tensor. So finally, you can cook up some way of multiplying together the uniform triple product with this difference between choices to get a linear map taking values in degree 8. And staring at this somehow the most complicated part in the working with these Pythagorean-Messe tensors is understanding how this transformation rule works. But the upshot is that if you change your choices of co-chain representatives, you can express the difference between the Pythagorean-Messe tensors as this linear map that you cook up in some kind of quadratic way from the difference between the two choices. So the uniform triple product depends in some kind of affine linear way on the choice, whereas the Pythagorean-Messe tensor depends on some kind of affine quadratic way on the choice. So affine quadratic functions, that's a little bit complicated, but you still have one single formula that tells you what the transformation rule is. So it's complicated, but it's something that's manageable. You can actually work with this in an example. And one nice consequence of this transformation rule is that if there is some choice such that the uniform triple product vanishes, so if there's some choice that makes all the triple products vanish at once, basically, then the Pythagorean-Messe tensor takes the same value for all those choices. Hence, you get a canonical canonical representative of the pentagonal messy tensor. And that in particular happens if you have a closed manifold where the Bianchi messy tensor is 0. So the final stage is then to say, how do you express functoriality for these pentagonal messy tensors? And to do that in general, basically also involves a similar transformation rule. So if you want to express functoriality, you have to say, you make a choice on one algebra, you make a choice of cochain representatives on the other algebra, you have this homomorphism between them that allows you to compare the two choices, and you get a relation between the pentagonal messy tensors that looks similar to the transformation rule that expresses the dependence on choices on a single algebra. So basically, the transformation rule that I showed you on the last slide is something you can obtain as a special case of this functoriality proposition by taking the homomorphism to just be the identity map. So if you specialize this to when phi is the identity, you recover the transformation rule that I showed before. And once you understand the functoriality behavior of the pentagonal messy tensor, then you can formulate a conjecture to say that in a dimension, if you have an S-connected manifold in a dimension range where 5-fold messy products can't play a role, so for instance, simply connected 8 manifolds, then an isomorphism of the cohomology algebras should be realized by a rational homotopy equivalence, or rather a zigzag of rational homotopy equivalences, if and only if, well, all the sort of formal consequences of the functoriality rules are satisfied. So that's where I wanted to get to. Thank you.